Thank you. Test. All good, I guess. Okay, so welcome and good morning. Thank you, RITMO, for organizing this already amazing symposium and allow me to stand here and talk with you. I hope you had a good night, good evening last night. I had a wonderful day. I have, I think, about 50 minutes, so that's quite a while, so that's nice, but I also have quite some things to cover, so I might go quite quick. Feel free to raise your hand or just interrupt me throughout the whole talk. If you have a question, you want to delve deeper, I'll go quite fast in the hope that I finish early so I can delve in deeper in some of the elements later. But okay, so as an introduction, as a researcher, we can say that technology enables us to perform well. Like almost you could say that we're as good as technology allows us. Whether we're working in the art, design, science, or engineering fields, technology allows us to capture and record, make closer observations, and use new analytical tools to make our findings and our observations. So I'll just give a few examples that everyone knows, but of course, when thinking of the microscope and the electron microscope, it allowed us to investigate closer, look at cell structures and things like this. Think of this technique, the dynamic lamp, that I'm sure you're all aware of, that allowed us to model the voltage potentials in neurons, another great technological invention. Think of this awesome picture of the particle accelerator in CERN, allowing us to make observations at subatomic scale. Or think of this another awesome technology where the James Webb Telescope, launched not so very long ago, allowing us to make observations at cosmic scale. And then think of all the computing power, the increase in computing that we did. Technology has advanced so much, allowing us to work with artificial intelligence and think of new paradigms using those. Well, this is quite, of course, the introduction, but what if we would have a technology that would allow us to immerse users in multisensorial environments, design and control affordances inside those environments, and deliver impossible stimuli or induce body illusions? Well, that's not so, and importantly, while promising the illusory sense of non-mediation, meaning that technology becomes sort of transparent, like you are in this environment and you sort of forget that you're seeing through a technological lens. Think of when you're listening to a concert and you're being so immersed into the audio in the composition that you sort of forget that you're listening through speakers. The realism becomes so convincing that it creates this illusory sense of non-mediation. Well, today, and of course, it can be improved in many ways, but I'm going to talk about this technology called extended reality, the umbrella term for virtual reality, augmented reality, and so on. And specifically, I'll be talking and giving like a pipeline on how to use virtual partners, design them, and use them in sensorimotor synchronization research. So hello, my name is Bavo and Kerrebroeck. I'm a postdoctoral researcher in the sequence production lab headed by Professor Caroline Palmer, and in the input devices and music interaction lab of Professor Marcelo Wanderley at McGill University. And the research that I'm going to present also originated during my PhD work at Ghent University under supervision of Professor Pieter-Jan Maes. Okay, so, and 50 minutes, so I will just use my coffee to take some breaks. The context of this virtual partners paradigm, of course, it's rooted in the notion of interpersonal coordination that all of you are aware of, and that yesterday we had beautiful lenses and perspectives on, specifically sensorimotor synchronization as seen as a fundamental mechanism for such interpersonal coordination. Specifically also, what I'm talking about today is this notion of a virtual partner interaction paradigm, and combined with computational modeling, in the sense that the traditional sense is that we do our empirical observations and we make a computational model or a model fit afterwards using the empirical data obtained. now in this virtual partner interaction paradigm, you sort of bring this scientific model inside the actual empirical setting. So you're doing your research, you have your participants or your test subjects interact with the scientific model in sort of real time, allowing experimental control of the actual model that you're trying to build and develop. It's like learning by doing, or understanding systems by building them. It's a bit in this philosophy. And these three combined, already a mouthful, but I'm going to combine them with extended reality, allowing an embodied interaction. So the real novelty of this technology is that it allows perspective taking and a three-dimensional experience, and can capture our actions, bring them into a digital environment with a lot of control, and feed them back to us in our perception through a multisensorial display. It can be visual, but of course also think of audio, and other interfaces for haptic feedback also exist, but I'm not going to obviously treat all of them today. Okay, so this is what I'm going to, and I'm going to look at the time, great. This is what I'm going to briefly illustrate. So this was the introduction part, and I know it was maybe heavy and big concepts and plenty of things to talk about for a long time. So now I'm coming to my more down-to-earth part of this, of the actual workshop. And what I'm going to try to demonstrate or show today is how we can create this virtual partner interaction, meaning you have a real human in black that is interacting with a virtual human in orange. And I just demonstrated, you see the person has a laptop in front of him, her, they, and they're just tapping on the space bar to indicate tapping onsets. So I'll just use my laptop to demonstrate it, but of course you could replace it by more interesting interfaces. And the drum onsets are going towards the virtual partner. It will listen to it and then synchronize its movements and its sound to the drum set that the human is generating, and it's being displayed in this VR goggles. This is the simple action perception feedback loop that we're going to construct. And since we're trying to do science also, there is this sort of experimental control that I've drawn on the side, where you use an external laptop. Today I'll just do it all on the same laptop, but where this laptop would allow some control, some parameter tweaking of the actual interaction. So these are all the things that I'm going to present today, so it's quite a lot, but like I said, I will go quite fast, but we can zoom in on any of those that you like. Yeah, and so we're going to start with the actual stimuli creation. So how do we create a virtual partner? Then I'll briefly comment on how to make the display work, how to show it in this head-mounted displays. Then a bit on the control, like the interface from control towards the feedback loop. The actual models, I'll give an example of a model that also has been mentioned several times yesterday, that you could insert in a virtual partner. A brief comment on some capturing, like how can you actually record data and what are the ways that you could do it. And then extras. So it's a long list of other topics that I'm happy to discuss also at later times. But first, let's start with the stimuli. Everything clear so far? Like I said, just raise your hand or just interrupt me if you feel a burning question or comment, critique, feedback, whatever. Let's start with the stimuli. So preparing this workshop, I just played my own test subject. But to create a stimuli, and you could make the stimuli from the ground up, but more efficient route and also more naturalistic route in a way. You would use a test subject, preferably an expert test subject, not your own, but for this workshop it did fine. And what I'm going to do is I'm going to capture my movements using motion capture to create my virtual partner. So to do that, I start, is it playing? Yes. I start by just making drum movements, because I've mentioned that we're going to make a drum interaction, and I just am tapping on an isochronous metronome, because I'm not yet wanting to record adaptive movements. That will come later. Right now, I'm just trying to create my my visual stimuli and of a just isochronous drumming. And so with motion capture, you capture using the reflective markers, you bring it inside motion capture software, and then from that software, quite simple, I could do all this in one afternoon, you export a file that you can then import in your into the next stage. The next stage itself is importing it into a software, and I'm going to use Unity. So the game engine also mentioned yesterday. There are alternatives, but today it will just be Unity. So you import that file inside Unity. I'll show that in a moment. And then the first part of the fun starts, but this is a topic on its own. So you can delve very deep, but if you do it simple, let's say, it's quite... it's not so complicated. So already you see a scene that I'm prepared, but I'm just going to do a new one. So this is Unity, the game engine software. It's to develop games, 2D, 3D games and whatever, but I've used it in the past years to design or develop my experimental scenarios. So I just start with a completely empty scene, there's nothing there. I always like to put in a plane so I can know where I'm at, so where's the origin and so on, so this is all clear. And then I put it in the center, and now I go to my mocap animation that I've just imported here, so this was just a couple clicks from the first part of the software, and then I have a sitting down, a part where I trimmed the motion capture recording to just sit down, and actual drumming. So I'll just do the drumming, and sorry, I should not first... This is the part that has my animation data. So you can see the guy here. So here is me drumming, but it's just the standard person that you get inside Unity. To actually use this animation, I'm going to import a virtual human. So I'll do this, and here is my virtual human. That is standing here on the plane, so great. So far, this is just a visualization of a virtual human. So he, let's call him he, is not doing anything. To then make him do something, and I don't know for purpose of time how much I will do live and how much I'll just do, like skip some steps, but this part I think I can already do. So what you do is you insert the controller inside the virtual human, and this is like a state flow diagram in which, when I click play, so now I'm already playing, here this animation starts playing. So you see it's a state flow diagram, so this first animation that I've just imported is now just playing on repeat, and here he is. You see already that the guy is sitting inside the ground. This is because my reference level for the motion capture, I had to place it a bit higher because the cameras and the angle were not good. I did everything like quite quickly, just to show all the steps, also during the motion capture, but you can correct the stuff later. So right now I'm just moving him a bit higher, and this is me drumming. So that's already quite nice. I took my data and I have myself drumming here. Let's call this the first part of the stimuli. Like I said, there's a lot inside this phase. So I showed you this virtual human called humanoids. There's this notion of skinning and rigging. Rigging is related to the actual skeleton that is used inside the animation. So it's basically a labeling that you use. Every skeleton part has a label that is referenced by the motion capture data. That's rigging, and then skinning is the actual rendering, the visualization. So now I used a guy, but I could, for the same purpose, use a woman or another avatar or a non-humanoid rendering, and import my animation inside that. What is also nice and probably good to show is that obviously you don't need to make them realistic. Can I change them? Let's just do it very ugly. So right now I just removed the color of the clothing. So to make my stimuli more neutral in an actual experimental setting, I've often used just gray avatars and removed all the more realistic elements because they can also, of course, bias or influence what you're trying to observe. Okay, so that was the skinning part. We had state flow diagrams and then inverse kinematics. I'm spending a bit more time on this. Inverse kinematics relates like you can actually manipulate the movements of your avatar, and the program itself will use inverse kinematics to correct for your things. I will not show it because it will take a while, maybe at the end if you have time, but basically what you can do with this virtual person, if I want to rotate the hands, you will see that I didn't do this correctly in my motion capture. If I want to rotate the hands, I can just rotate one part of it, and the software will correct all the, do some inverse kinematics automatically and correct the elbow position, the shoulder position, and so on. So that's a very useful thing that I'd like to mention. This animation and avatar, so I've been using, and it's good to reference them, I used a database from Microsoft. So in this database, the Rocketbox software, it's all open, it's Creative Commons license. And here you have all the avatars, also the two that I've just shown before. So you can pick your own rendering and then import that one and use it as a stimuli. And then Mixamo is another useful library because it's a library that has a lot of free and paid, but also a lot of free animation clips. So if I want to just add, for example, I've used in the past, if, for example, a participant starts wearing the headset and wants to wait in the virtual environment and you have this very static avatar, it's nicer to have an avatar that's maybe just sitting idly and just waiting. So here, by using sitting dodges, this is for a game, obviously. Sitting gun motion, yeah, this is also not what you want, but there are all these like sitting animations that you can just use before the actual experiment starts. And combining animation. This has been useful for me as well, like sometimes finger movement, very hard to track using motion capture. There's also a way to combine animation. So what I've done in the past is using a separate tool, a leap motion, to capture my finger movements, use that animation and blend them with my body animation. That way you can actually introduce finger movement. Okay, so that was quite a long part on... Yes, of course, yeah.
Sorry. No. How does Unity do with inverse kinematics of something a bit stressed, like, say, playing the violin or playing the trombone?
Good question, and I haven't tried that. For me, it was simple rotation, so I'm not. Try it out. I'm curious to see, but my guess is it's really used for the more gaming, and it's based on human motion and not there are not so many violinist games, so a lot of the motion is purely on human things. Like the best thing, and I can show it maybe at the end if there's time, is just rotations and moving. Also head gaze works very well. So for example, you can put an object somewhere and your virtual character will just follow it, and the shoulder and the neck and everything looks very realistic. It's not like this thing. You actually have a nice posture that also rotates along and so on. So it's more for this kind of gross human motion than actual fine-grained violin stuff. Yeah. Okay, then we talked a bit about the stimuli. Let's go to the display. There are many displays, so there's this VR part, and now there has been this move, maybe you've heard also, that Apple is creating its own headset, and lately, like Dana was so kind to borrow me the new Oculus, which is a mixed reality headset, and there is a move of these commercial companies towards more mixed reality, so offering both virtual and augmented reality, which is nice because with virtual reality, the advantage is that you completely exclude the real environment. The user is completely immersed in a virtual environment, but it's quite intense, let's say, as an experience, so it's like all or nothing, while augmented reality allows you to place a virtual object inside a real environment, so the user still sees and feels present in the room, but then you can administer a stimuli as a sort of hologram. So this new headset, if you want to try later out or throughout the day, I will manage the headsets for today. Thank you, Dana. So you can come to me and I can demonstrate. when you start developing, there are several frameworks that you can use. OpenXR is like a cross-platform framework, because if you start developing this stuff, calculate some time to just spend a lot of time searching for the right click button or the right checkbox to fill, or the tutorial online. All these frameworks and all these brands have their own software packages. So Oculus Integration SDK is a good one that I've used for the Quest, but you also have, Microsoft has its own toolbox, and OpenXR is cross-platform, so across toolboxes. I just want to show like the Oculus, not to promote this kind of thing, but they did, their documentation is really good, and also they have very nice tutorials, so you're just following the steps here, and really, with nice screenshots and everything, you follow all the steps, you don't have to think, basically. In one day, with a headset like that and a good enough computer, you're off. The good enough computer is a good comment, because also there you have to actually stream from your PC to a headset, you need a powerful enough GPU. So this laptop cannot do it. You need a strong laptop or a desktop PC to stream towards a headset. With my not so powerful GPU here, I have to do I would say parallel route. I have to build the application on-site the headset. That's also possible, but it requires a few extra steps that you do, and just following tutorials online allows you to do that. But that also means that later when I demonstrate the actual app in the headset, I cannot stream it in real time on the projection, because I built the application on the headset. So it's like an app residing on the headset itself. That's all I'm going to say about, there's more to say, but okay, so if we had the stimuli, we know a bit about the frameworks on how to build it on a headset, and now I'm going to talk about the control. So if we have our person standing here, and I'm going to cheat a bit, and I'm going to use the scene that I tried, which one is it? That I started preparing, that's empty, I think. To make the communication, what we're going to do, I'm going to use pure data to communicate with Unity, or later with the headset itself. So it's using the OSC protocol. It's a protocol to just send data using IP addresses. So inside my Unity app, I just use another open source library, which works very well. And also here, nice screenshots, and there's not even a tutorial because it's almost so simple. It just has a couple of files that I can show. You use this library, you import it inside Unity, you create an empty game object, and maybe I'll just do that. So you create an object in Unity. This is empty, there's nothing in there. And then I've downloaded the files, it's only 3 files from this open library. I drag it in here, I have an IP address and a port from where it receives data. So right now, Unity is already ready to receive data from an external program. And I'm going to do it all from my PC, but if you would have a separate PC, it would also work like this. So inside pure data, there's, of course, more things to say about pure data, but it's a visual programming environment that just allows me to, like every block that you see is a bit of code, and it's just an interface. Like you can create objects and numbers and remove them and connect them using these cables. So it's easy to just quickly build a small program. What this is doing is basically just taking the average of my taps. So every dot that you see is me passing the space bar. And basically what is inside here, it looks complicated, but it's just a moving average, so tempo detection basically. It's just calculating my tempo. So now I'm tapping at 2.3 hertz, okay? So it takes my tempo, and here I'm sending it through OSC to an IP address, and I have to connect it. So the IP address 127.0.0.1 means just send it locally, send it to this PC that my own pure data patch is running on. So I'm just going to connect it here, and then the port is 1234. That's important because I need to put the same port here. So right now they're already communicating data to each other. they should be when I launch it. But of course, when this data arrives, the program in Unity doesn't yet do anything with it. So therefore, I'm going to add a script, which I called OSC input. And I'm going to show the script, which will take a while to open. Because also there, it's very, I should stop saying very simple, but it's not so complex. Okay. So you see, this is the script. It has a variable that just says to me, like, refer to the object that I'm going to use to communicate outside of my program. The animator, so that's my the state flow diagram that I showed before. And here, when launching, I'm going to collect my animator. I'm going to set the speed of the animation to 0. And then for the OSC object, I'm going to print test. So it's actually print test that is the address here. And then print test calls this function, and this function then sets the speed of the animator. So right now, with this script, with all the steps that I've shown, I've already allowed my spacebar to control the tempo of my virtual human. So here it says I'm missing because I have to indicate where is my script, so that's good. But what I remember from here is that print test is the address that it says here, so I need to insert that in my patch. So it's not speed, but it's called print test. And now let's hope. Beautiful thing with demos is that they never work live, so let's see. But already what is working is that the speed of my avatar is indeed, he is not playing, but now I'm connecting to my Unity thing, and now I should, or I hope. Yes, so we have our thing that's now adapting to my tempo. So that's very simple. So that's nice. I already have a tempo adaptive human, and if I would be building this app on my avatar, I would have a tempo adapting thing. And these were all the steps that you needed. So that's great. Of course, there's no synchronization yet. That will be the next step. Okay, so great. We already have like this external patch now that receives input from my tabs. And maybe another thing that I can do and illustrate. So I did it from my tabs, but actually, so basically what I've shown now is this part. So it's me tapping on the PC, receiving the input to the avatar. I want to show the control. So I'm using the same PC as both control and input, but imagine that I'm now going to PC2, and I'm going to control. Because, of course, I can change the parameters of this avatar. I could change the scale, the color, if I wanted. I can also change the tempo now manually. So just using this parameter here, I can set the tempo to, and I'm sorry, but I'm going towards 3 Hertz, or 1 Hertz, or stop, and so on. So I'm basically showing you the same thing, but it's just to show that it's useful to have this kind of control. With bit per data, you put your objects inside, and you can trigger stimuli inside an experimental setting. That's how I've been using it for the past years. Okay, so we've had stimuli, we've had a bit of display, how to build it, and then some control. Let's go to the next step, which is, the model part. So this is what we've shown. And now we're going to make the virtual human a bit smarter. So we're going to insert a computational model inside the virtual human. You could do this inside the Unity program, this game engine environment, do it in the code, the C# script, but actually I'm going to, again, cheat because it's easier for this purpose. I'm going to put the model on the laptop. So on, you don't see my, here you see, yeah. I'm going to put the model on the PC part, so it's on my pure data patch. As introduced also yesterday, I'm going to use the Kerrebroeck model inside the virtual human, and very quickly, basically you have phase speed, so the speed at which the human is tapping receives an intrinsic frequency, so a tempo that it is most comfortable at, this oscillator model, and then K is a coupling parameter that is important because it will tune the adaptivity of the virtual human, and then a coupling function that calculates how and what manner they are adapting to each other. There are many variations and extensions. You can look in the references, which are interesting. And I'm going to show it briefly. So first what I do is I try this model inside my pure data patch. So we're going to leave Unity and our virtual human for a moment and open a new patch, basically a a continuation of the previous one. And as you remember, so here's my input, my spacebar input. And I also have another input, it's another key, it's the dash key. I have two moving average, so in red, basically what it does, it calculates the average of this tab that comes in and then creates a signal, a frequency signal from my tabs. Basically, it samples it at a very high sample rate, what I'm doing. And then in blue, I have my computational model, and this is all that I had to do to implement it for this simple purpose. It's just the formula that you see, the sinus here, the coupling parameter that comes in here, the intrinsic frequency, and so on. So before trying out with your human, an engineering principle is to develop in modular ways. So first what you do is you do the modular ways, and here. So okay, I'm just going to tap a bit smaller. So basically what you see, I have two oscillators. The black and the blue one, and so one is rotating at tempo 1.3 and the other is at 1.29, and the coupling is too low. I think it's blue that is controlled by the Kerrebroeck model. But the coupling is too low and the intrinsic frequency is too far apart from the reference. I will not go too much into detail, but basically, if I increase the intrinsic frequency, so maybe I can do, blue is indeed my Kerrebroeck model, so I set the frequency to 0, so it's most comfortable at 0, but still it's pushed and pulled a bit towards the oscillator that's coming from my spacebar. So I'm going to set the intrinsic frequency to 1, okay. And now I'm going to increase the coupling, because actually I wanted to adapt. And now if I increase the coupling, nice, they're going into synchronization. There is still a phase lag between the two oscillators, but the more I increase the coupling, the smaller this phase lag becomes. And now if I tap slowly, for example, you see that it will adapt. The coupling is way too strong, so it's not even interesting at this level because it's superhuman synchronization. But now, okay, that's a nice thing. You see how it moves towards the red dot and it tries to synchronize with it. So okay, that's all I need to demonstrate here. The computational model is working in my pure data patch. Great. So now the next step is to integrate all of those. So what I do then is to, if you remember, I had my avatar here that was tempo aligned to my space steps, and now in my pure data patch I had this model that was synchronizing to my space step, the blue dot. So basically all I need to do is to connect the speed that's coming out of my oscillator model with this avatar guy, and then the avatar should play with me. So, okay. So the only components that I've added here, I put it orange for some sound, but we have enough things going on, so that's not so important. It's sound in orange. And then in purple, it's again this OSC connection, so an IP address and a value for how to print test. That was the address that this guy was listening to. Okay, so everything here should be fine. So I'm going to reset, I'm going to start. The agent oscillator is already rotating. And this is way too, Okay, so this is rotating, good. This guy is not yet responding because I have to launch it first. Up, great. And then now it's still not responding because I have to connect it using my OSC. So I say, listen to this IP address, and right now the guy is indeed synchronizing. So the tempo of this oscillator now is being sent to the guy, and the guy should be, I think also the tempo detection there is a mistake there because suddenly it switches to 0, but it's already synchronizing. So you see on the top, here, on black here is my spacebar. that's coming in, and black down here is when this guy should be tapping, because it's when this oscillator reaches 0. It might be, I'm going maybe too complex. Afterwards, ask me questions and I can show it slowly during breaks or whatever. But this guy is synchronizing, so nice, yeah. And like I said, there's something wrong with the tempo detection because suddenly it drops to 0. When it doesn't remove outliers. When I don't tap for a long time, it slows down too much. But okay, great. So basically, we have what we need. Awesome. We have the integration, and everything is working, so nice. But, of course, maybe no, first the next part. But, of course, now that I've shown you this all quickly, when working in digital environments, something that you don't always see clearly put, but latency becomes a very important issue when designing this kind of stuff, because right now there's already quite some signals going on, and when you're using external hardware and a consumer PC and a Wi-Fi network and whatever, latency and synchronization becomes a serious issue. For example, with my taps right now, I'm only synchronizing the speed of the avatar to my taps, but there can be a drift. Like over time, if there is a little bit of a delay or the sampling rate is not adjusted accordingly or whatever, the avatar can speed up or slow down and no longer be really attuned. Like the pure data patch, the oscillator that's going there might be out of sync with the game engine. So there are several ways to do that. Like the simplest thing is to send signals from both programs and saying, hey, I'm here, I'm at the start of a cycle, make sure that you are too, or correct for it. So there is one way to do this synchronization between the programs from pure data to Unity. You could do a single cycle animation. So instead of recording a full length animation of 2-3 minutes or longer, you just record one cycle. So basically just one tap or two, and just put those on repeat. That would be the easiest because you always know exactly, like it's one cycle, so you exactly know when the cycle has ended, and you can tell pure data, I'm at the end of the cycle now, make sure you are too. But of course that doesn't create a very realistic stimuli. You don't have any variations. The virtual human would always be doing the same thing. You don't have the nuances of a person doing, a 1 minute drum thing. So multiple cycle animations that you can do, and I don't remember what was the trick that I plan to use there, but I'm going to do this, the other part where I do the synchronization from Unity to pure data. So what is nice in Unity is that you can create events in your mockup time series. So I'm going to show that a bit because also that's more difficult to find if you start to develop this stuff. So if you remember, this was the animation that I was importing, and here I have the actual animation. I can open this, and here I have my actual mockup data. So as a mockup, I have everything. And so left foot, head, chest, neck, and whatever. I can go to the curves and make it rub. Yes, there they are. I don't know why. Okay, because I just selected one of them. But if I select all of them, yeah, that's way too much. But here are all my signals. These are actual samples recorded coming from the mockup data that I imported inside things. So that's good. And what I can do, I use it to actually synchronize the mockup to my pure data patch. What is nice is you have these oscillations here. So a good part to look at is the left and the right hand, of course, because they will be most indicative of when a cycle is starting or ending. And you have left hand. You have several left hand parts. Left hand down, up, in, out. So two. But I think in, out is the best. So I use my left hand, and then of course also the right hand. So right hand in, out. Right hand in, out. Thumb, no. Here. So these are my two hands. So that's nice because I see clearly this is a cycle. So this is my right or left hand going up in red, and then the other hand going down, and then the other hand going up, and so on. So you nicely see the time series of your data movement. And what I've done here is place events. So I think at animation events, you can give it a name. Here, send onset is the animation that I've placed at every tap. So send onset is here. I already did it for the full cycle here. Yep. And then, where's the script? It will not be in this one. Oh, damn it, I just moved a folder accidentally. Where's my script? Okay, script. I think it's OSC input. Reload. Sorry for that. Yes, or it will be control animation, I guess. Yeah, so here, send onset. So already inside Unity, because I created an event, if you remember, called send onset, automatically throughout Unity, an event is triggered. An event is basically the whole program can catch that event. And basically it's searching for the right function to trigger, and here in my event send onset, I'm sending an OSC message called onset, and I send it out. And then inside Unity, in my OSC part, I have my out port, 6161, and to make the two programs synchronized, what you do, so I just open a patch because to save myself time, I did this before, I listen. So here inside Pure Data, I have an actual open port. This was 5678. So I should put 5678 here. And then inside Pure Data, here 5678, root onset. So when this guy will be playing, but it will not be this guy. I think it will be RUP. To actually make this guy give the output, I have to drag the script to it. Control animation. I think this one I can put out. Oh, damn it, I made a mistake. Non-OSC, so this needs an OSC thing. I don't exactly remember what is in control animation, so I hope it works, but okay, the guy is not playing now. So here in this patch, I reset it, I enable signal processing, and hopefully, no, it's not going to play yet because I have to connect it. 1 to 7, so now it's connected, great. But unfortunately, there is nothing coming in here, 5678, 5678, root onset. I was thinking it would be good to have such a moment because it allows me to show how to debug programs. Listen, I have to do listen. Why isn't... So right now there is nothing coming in my Pure Data program. Maybe I have to first launch Pure Data and then I'm not sure. No, it will not be this. Okay, I'm just going to leave it for now. And I'm going to cheat and open the scene that I prepared in advance. So it was, oh, why isn't this working? Okay, normally I should be able to rotate. Come on, sorry. My mouse is doing a bit weird and I cannot rotate anymore. Yeah, I can use this normally also, but no, it's like clicking. I see two mouses and I cannot normally, but okay, it doesn't matter. Yeah, in any case, she's drumming, and what is nice here is that in this root onset, that these dots that are coming in, they're actually coming from Unity. So for example, if I set the tempo to 0, let's call it reset, these things are stopping. But if I start it again, so every time, and normally I could rotate the camera, but every time it is drumming, you get an onset inside my Pure Data program, allowing me to synchronize both data streams. But I see that I only have 5 minutes left, so I'm sorry. There are many more things to say, but this is how you show when you finally build it inside Unity. You launch it, So now I'm wearing the headset and I took a video inside, and I have the woman standing there. I think I'm going to show what is nice in these VR goggles now also. This was in the past more buggy, but now you also have very nice hand tracking. So I think I should be showing, showing my hands. Yes, okay. So you have very nice virtual hands, which is already, if you've never done VR, I find just seeing your virtual hands already an experience. And basically I'm now showing, I'm using my space bar, wearing this VR headset and looking at the human that is synchronizing to my taps. Okay, I'll just go very quickly for the last 4 minutes that I have. Questions or reflections we can talk afterwards. Because just 2 words on the capture component, like pure data, there are 2 ways where you can do this data capture. You could do it on the external PC in a pure data patch, or you could do it on the headset itself. So this is an example of how to do it in pure data. On the right, you can see a script. You just write a text file, and it's generated on the headset. There are advantages and disadvantages to both, like sample rate. If you want to use it on your PC, maybe it's more safe, you see the data coming in, but latency again. Sending data is then more costly. Doing it on the headset, you have to pull it out afterwards every time. And then there are many extras. So social and environmental stimuli. This nice thing, now I've showed a social stimuli, but this morning I had some fun trying to change the environment of the human. So now it's just a simple sky, but I tried to make the sky a bit more interesting, and I hope I can rotate the camera now. No, I can't. That's unfortunate. But okay, you might recognize, it's a video of Oslo playing, but it's unfortunate that, like, I don't know, maybe. Yeah, normally I should be able to rotate my view. But normally when you wear the headset, you're in a nice 3D scenery of a 360 video playing. So you're drumming with the woman while standing in the center of Oslo. And it's of course very weird because if you're standing there, I just picked this video from a YouTube channel earlier. So, but this is a way to change the actual environment. So with VR, it allows you to also change the actual environment that you place your participant in. There's the thing to say to real-world alignment, which is a pain. In VR, just putting your user inside, that's nice because you might not care, but as soon as you want, haptic stuff, you want people to interact with the real environment, or you want to align them, then it becomes complicated. There are ways to do that using motion capture or spatial anchors. Usually explained in the documentation of all these headsets. Multi-user is a thing, like there's a Photon engine where you can use multi-user. It's another software package that you can use for that. I haven't talked about audio. Spatial audio is a big thing in these headsets, and there are a lot of frameworks for that, so that's interesting and a lot of things to do there. And then for actual capturing, there's so many ways to actually capture data. You could integrate a sensor or sensor data. As you've seen, it was just running on a pure data patch, so just connecting a sensor to my pure data would allow that. And then there are very interesting new paradigms that this tool allows, from body swapping to mirroring paradigms, and using this multi-user setup, also investigating group dynamics. Final note, so 1 minute left. When doing this stuff, it's good to remember that like I've shown you the whole pipeline, and it's quite impressive today that just with some consumer-grade material, you can already start building this. With quite some discipline and think you can quite easily do this, but the trick is not to do everything at once, to just do it in short cycles and quickly feedback, like I've shown you how a modular approach works. KISS is like keep it simple, stupid. So keep it simple as you need to. Don't make it overly complicated. And stupid is meaning like make it so that the naive user can use it. That's nice because these pure data patches, I can hand them over to a research assistant, create the buttons and create the interface, and so anyone can actually work with it. Fail fast, fail often. So you see me, once you struggle, once you run into a problem, no problem. Just continue, fail fast and fail often, and learn from your mistakes. And then beware of the rabbit holes, because when you delve into this stuff, there are so many interesting and things to do that be careful that you don't zoom in too much. Just stay maybe exploring a bit. I placed the pure data package and a link to the actual Unity package in GitHub, so you can go there if you want to try. And feel free to add me on LinkedIn or contact me if you have any more questions today or by mail later. Okay, thank you.